All right, hi everyone. Welcome back to the second remote lecture for NETS 412. I'm gonna unmute you all for a second so we can say hi.
Unmute us again.
Hey everybody.
Hello.
Hello. Hi.
Hello.
You guys can say hi too. All right.
Hello.
So let's begin. So if anyone can remember back to the last time we had an actual algorithmic game theory lecture, which I guess was nominally 3 weeks ago, but at this point feels a lot longer ago than that, before the global pandemic. We were studying mechanism design, and we had spent a lot of time thinking about mechanism design in a setting in which we weren't allowed to use money. So just to sort of recap, the first half of this class, we studied game theory, which is really the study of predicting what people will do in a game, right? Like, given a complete specification for people's utility functions and their action set, how much they like different outcomes and what they're allowed to do, we studied various ways to try to give computationally plausible predictions for what they actually would do. And we saw that, for some things, you could make good predictions. So when we started the second portion of the class, what we're calling mechanism design, remember, this is really sort of reverse game theory. Now we get to design the rules of a game so that when people act in the game, the outcome that's actually realized is the thing that we want. And we saw in a couple of settings you could do this by introducing what we call mechanisms, sort of means by which people can interact in a game to lead to outcomes that we wanted, even without needing to use money. Right? So we saw this for Pareto optimal exchange problems, which are used for kidney exchange, and we saw this for stable matching problems, which are used for school assignment and assignment of graduating medical students to their first residencies. These are both settings where we don't want to use money, and yet we would like to design and deploy mechanisms that coordinate potentially self-interested rational people towards good outcomes. But these were really sort of special settings. These were the exception rather than the norm, where we could design mechanisms that induced games that would lead to good outcomes without needing to pay people or to take payments from people. And most problems, actually, it turns out, you can't solve without the use of money. So in this class, we're going to introduce for the first time a very general tool for solving mechanism design problems. It's going to solve mechanism design problems in an incredibly broad and general setting, as we'll see, but that crucially makes use of money. Okay, so this will be, it's going to make use of money to align people's incentives with that of the mechanism designer so that they do what we want. And it'll be a very general setting, but maybe like the canonical example of a mechanism design problem is really a simple auction design problem. So maybe if you want to keep some task in your mind as an example, just think about auctioning off a single valuable good, right? Maybe I've got like a roll of toilet paper and I'm trying to figure out who to give it to. I'd like to give it to the person who values the toilet paper the most. I don't know who that is, and we're gonna use an auction to try to solve that problem. So, keep that simple example in mind, and we'll talk about a couple of other sort of instantiations of this framework. But I want to start by defining the general setting in which we're going to work. Okay, so sort of in the general setting, there is some set of alternatives that we want to choose between. Okay, and we're going to think about these alternatives as a completely abstract set A. It's just some decision that society or we want to make. And we're not making these decisions in a vacuum. There's n agents out there. There's n people, players in the game that we're eventually going to induce who have opinions about which of these alternatives are the best ones. So the way we're going to model that is the way we normally do. Each of the agents, and we'll index them by I, will have some valuation function. And a valuation function will just be the function that represents for each of the agents I how much they like each of the alternatives. Okay, so as usual, we'll think of it as some function, one for each of the players, mapping alternatives to non-negative real numbers. And higher valuations are better than lower ones. And what we are going to try to do is we're going to try to design a mechanism, design an algorithm which is going to induce a game in this setting that will take as input people's reported valuations and will choose one of these alternatives. But as I mentioned, we're going to make use of money. So we're going to choose not just an alternative, but also a pricing scheme. And we'll call that an outcome. So an outcome is a pair of two things. One of the alternatives from our set of alternatives and a payment vector. And a payment vector is just n numbers, one for each of the n agents, specifying for each agent I how much they have to pay to the mechanism. Okay, and potentially these numbers could be negative. So a positive number, if PI is 2, that means agent I has to pay me, the mechanism, $2. But if PI is negative 2, that means that I, the mechanism, have to pay agent I $2. And finally, just as we assumed when we were studying market equilibria, we're going to model agents as having quasi-linear utility functions, which is a sort of standard thing, not entirely without loss of generality, but essentially the assumption that we're making here is twofold. First, that the agents can express their value for the different alternatives in dollars. Okay, so it's possible for you to express how much you value each of the possible alternatives monetarily. And second, that your utility for money is linear. That is, if I double the amount of money you have, you will be twice as happy. Okay, that's generally not true. If we cause the amounts of money that we're dealing with to be, incredibly large, but isn't a bad approximation at a small scale. I've got a question. The question is, can an outcome also have a lottery over alternatives and not just one alternative? So a mechanism can certainly be randomized. So, let's say yes. The way we're going to use notation is an outcome will be a deterministic alternative, but a mechanism, if it wants, could choose a lottery over outcomes. So we're not going to use this power in this lecture, but certainly, when you're designing a mechanism, it is in your design space to flip coins and use randomization when choosing outcomes. Good question. Are there any other questions about the model while we've got this up on the slide? And just to sort of finish up, the assumption of quasi-linear utility functions means that I'm going to assume that I can write anyone's utility for an outcome as the difference between their value for the alternative minus the amount of money they were asked to pay. A couple of other questions, good. First, is an alternative a set of goods? So we're going to talk about instantiations of this general framework in a slide or two. And yes, like if we were using this framework to model, for example, a multi-unit auction, then an alternative could be an assignment of goods to people. So it could, your value for an alternative could be your value for like the set of goods that perhaps the alternative represents that you get. But at the moment, we're defining an extremely general setting. So an alternative could be any number of things. An alternative could be, for example, like a policy that Penn adopts that has implications for everybody. Like, maybe one alternative is that all classes are pass-fail this semester. Another alternative is that pass-fail is optional. Another alternative is that grading goes on as usual. Another alternative is that we start grading more harshly. And different people might have different valuations for these alternatives. So at this level of generality, because we're thinking of these alternatives as a completely abstract set, they can really represent any number of things. So the framework we're laying out right now is extremely general purpose. It can model all sorts of stuff, not just auctions in which people get stuff, although that's a good example of where this framework is often used, but decisions about whether to build a library in the town or not, decisions about how we should set policy at a school or national scale. Another question, what is the p-vector? Can multiple people receive or pay for the same alternative? Right, so what we're gonna do is we're gonna choose an alternative, okay, in this abstract setting, and then potentially, everyone will have to pay or be paid something, right? So the alternative, everyone has some value for the alternative, and everyone has to make some payment. And different people might have to make different payments, which is why P is a vector. It specifies the payment that each of the n people might have to make. A question, can I repeat the first of the two implications of agents having a quasi-linear utility function? Yeah, so these are basically assumptions we're making, right, to justify why the utility function can be written just as the difference between the value of an agent for the alternative and the price the agent is asked to pay. Okay, and the first is maybe a smaller assumption. It's that the valuation function can be sort of denominated in dollars. I can, decide that my value for some alternative is equal to some amount of money, that these two things are even comparable. And the second is that your utility for money is linear. Good questions. All right. So, okay, we talked about this a little bit, but let's just note for a moment that this is an incredibly general framework, and so it can represent many things. So for example, maybe the sort of canonical example is a single item allocation. I have one roll of toilet paper and I would like to, assign it to the person who values it the most. In this case, the alternative, right, that I choose is the name of one of the agents, right? The thing I'm going to choose is who gets the toilet paper. Or it doesn't have to be like a single item allocation problem. It could be a multi-item allocation problem. I might have many things. I might have, hand sanitizer. I might have toilet paper. I might have corn husks. And I can allocate bundles of goods to different people, in which case the alternative would be like a full allocation, a mapping from people to goods. Or it could be a public goods problem, right? It doesn't have to be a problem where I'm assigning things to people, right? I could decide as a town, are we going to build a library or a fire station or a hospital? It could be a policy problem. We already talked about grading policies, for example. We can be choosing among any set of alternatives that people have opinions over. Okay, so at the level of generality that we've defined the problem, you can cast almost any choice you need to make into this setting. Okay, does this make sense? Do people sort of understand how in general, like this abstract setting can represent all of these things? So that's the setting in which we're operating in. And our goal as mechanism designers is going to be to come up with a mechanism that will choose somehow like a good alternative, right? So what's a mechanism? A mechanism is just going to be some algorithm, some function that's going to map the agent's reported valuations to an outcome. Okay, so our like algorithmic design space will be the following. People will report to us their claimed valuation functions, and then we will, you know, aggregate all of those, think about them, and our algorithm, our mechanism, will choose a hopefully good outcome. Right, so an outcome, remember, consists of two things, an alternative and a payment. And so a mechanism itself can be described as a pair of two things, right? There's a choice rule, which we'll call X, and this is the thing that will, as a function of all of the reported valuations, choose an alternative. And there's also the payment rule. This is the thing that, as a function of all of the reported valuations, will choose a vector of payments that'll specify for each person how much they have to pay. And any choice of these two things, you know, any choice rule we might come up with, any payment rule we might come up with, yields some mechanism. And as we've talked about before, right, when we introduce a mechanism into the setting that we've defined, we induce a game, right? Because all of a sudden we have an action set. The action set of each player is the valuation functions that they can choose to report. And we've got a utility function that players can evaluate over any set of actions that the players might choose in the game, right? Because for every vector of valuation functions that might be reported, the mechanism will choose some outcome, and the players, the agents, have utility functions over these outcomes. So, right, so we get to design an algorithm, and we'll introduce the algorithm into this setting, and it'll induce a game. Okay, so remember, we want to design our algorithms that will induce games that have good properties. Like, we both want to have our algorithms actually, you know, select good alternatives, perhaps, right? Like actually solve some algorithmic problem well. But we also want them to manage incentives correctly so that we can be confident that the data that we are being given, that is being self-reported to us by the agents in this setting, is the right data, that they're not lying to us. So why don't we start by sort of laying out some wish list, right, of desiderata that our algorithm should satisfy. You know, maybe we'll be like a little too ambitious here, and we'll see if we have to give up on any of this. But let's start out by being greedy and lay out all of the great things that we might want our mechanism to satisfy. Okay, many of these are things that we've talked about before. So first, we want people to participate in our mechanism, right? Like in general, we cannot compel people to you know, interact with algorithms we deploy. We can't compel people to participate in auctions. And so we'd like to design our mechanisms to be safe to participate in, so that nobody ever regrets participating in our auction, right? We want to have some safety property. And the safety property we're going to ask for is what's called individual rationality. We've seen it before. And in this setting, we'll say that a mechanism is individually rational if for every agent I, no matter what vector of valuations everybody else reports, it should always be the case that the value that agent I gets for the alternative that our mechanism chooses is greater than the payment that the mechanism asks agent I to make. Okay, so the mechanism should never force you to pay more than your reported value for the outcome. Right? Like, of course, if you lie and over-report your valuation, it might ask you to pay more than your true valuation. But this is a safety property saying that at least if you report your true valuation to the mechanism, if you don't lie, then you're never going to be out money. Like, you will always be happier with the outcome, happier with the alternative chosen than sort of the fee that you were asked to pay. So the next property that we might want is another one we've seen before, and it's called dominant strategy truthfulness, or incentive compatibility. And the idea here is a simple one. Like, there's some algorithmic task that we're going to want to solve, like in a single item auction setting, we want to give the item to the person who values it the most. Right now that's a very simple algorithmic task if we have the data, right? If I know how much each person values the item, then giving the item to the person who wants it the most, that's just sort of computing a max of a set of numbers. That's trivial. The problem is that if I sort of naively go about solving that purely as an algorithm design problem, then I won't have solved the real problem, because I will have solved the problem on the reported data, but there's no reason to think that the reported data accurately reflects the true data, because people will strategically misreport their valuation functions if they can gain by doing so. And so dominant strategy truthfulness simply asks that nobody should have any incentive ever, no matter what, to misreport their valuation function. That in the game induced by our mechanism, truthfully reporting your valuation function should be a dominant strategy, right? So just sort of writing that out in math, what we're asking for is that for every player and for every vector of valuations that everyone else reports, and for every alternative valuation VI prime that you might consider misreporting, your utility for truthfully reporting your valuation should only be higher than your utility for misreporting. Or equivalently, if we look at the value minus the price that you experience for the outcome that's chosen when you truthfully report, that should be only higher than the value minus price for the outcome that's chosen if you choose to lie in any way. Okay, so if our mechanism satisfies this condition, then we can be relatively certain that the data that is reported to us is the correct data, because sort of, we don't need to expect much from the rationality of our agents. We only need to sort of expect a minimal level of rationality for them to realize that truthful reporting is the right thing for them to do, right? Because dominant strategy truthfulness is such a strong criteria, and you don't have to think about what your opponents might be doing. No matter what they do, you're always best off reporting truthfully. Okay, so our second desideratum is that people should always be incentivized to correctly report their data to us. And we'd actually like to design a mechanism that chooses a good outcome, right? Like, we could always choose, a random outcome and ignore the reported valuation functions, and that would be dominant strategy incentive compatible, but it wouldn't choose a good outcome. And so we might also want allocative efficiency, or in other words, we'd want our mechanism to be social welfare maximizing. This isn't the only possible objective we might have. We'll think later about profit maximization, but one nice thing we might want to do is to have our mechanism choose the alternative that makes people as happy as possible in the aggregate, that maximizes the social welfare. And what that means is that for every vector evaluation functions that might be reported, our mechanism should choose the one that maximizes people's sum happiness, that maximizes the sum of their valuation functions evaluated on the alternative that we choose. Let's see, I've got a question. Would a mechanism with p equals 0 for any valuation correspond to the matching framework from before, or a voting framework? Yeah, so The sort of mechanism design settings we've thought of already, in which we didn't need to use money, could also be cast in this framework. And the mechanisms we came up with always had these sort of identically zero payment rules. Nobody ever had to make payments, right? So all of that can be cast in this setting, but now we're sort of designing or we're defining a more expressive framework that allows us to use money, which is going to allow us to do more stuff. Okay. So we want our mechanism to choose a good outcome. Okay, and why don't we get greedy? Finally, we've already asked that our mechanisms be safe to participate in. We've already asked that they be dominant strategy truthful. We've already asked that they be allocatively efficient, that they come up with good outcomes. But in the end, we're mechanism designers, we're not saints. And so the framework we've defined, right, allows the payments to be positive or negative, right? We can collect money from people, but we can also pay them. And it would be a shame if the only way to achieve all of those other good properties was to bribe people, was to sort of pay them money, because then it would be very expensive to run the mechanism. And so we might also ask that our mechanism is no deficit, right? Later in the class, we'll actually think about, what if we actually want to make a profit? But for now, let's at least ask that our mechanism is no deficit, which just means that no matter what the reported valuation functions are, the sum of the payments across all of the agents should be non-negative. That is, in aggregate, the mechanism should not be paying the agents should be paying the mechanism. Okay, so these are a set of all, 4 desiderata that we might hope for, and now let's think about whether we can achieve them. So I'm going to go through like a simple example, but maybe this is another good time to pause and ask if there are any questions, right? So now we've sort of laid out the setting in which we're working in, right? Things we might hope for, and right, so we've sort of defined the rules of the game that we as mechanism designers are going to play. We can design the allocation function and the payment function, and we've defined 4 goals we might have in playing this mechanism design game. And I just want to make sure everyone understands that. So are there any questions now about what we're trying to do here? Okay, so let's go through a simple example to just get our minds on the same page. And it's sort of maybe like the canonical mechanism design example, a single item auction. Okay, so again, imagine I've got one remaining roll of toilet paper, and the thing that I want to do is I want to give it to the person who wants it the most. Okay, so let's cast this in the framework that we've been talking about. So first of all, our set of alternatives in a single item auction is just equal to the set of bidders, right? Like the thing that I'm going to decide is who gets the toilet paper. And in this setting, valuations are pretty simple objects, right? Like, either you get the toilet paper or you don't. Let's assume if you don't get the toilet paper, you get value 0. If you do get the toilet paper, you get some value, some real value. And that's the thing that's going to differ across agents. Okay, so valuation functions are functions, but let's abuse notation and think of valuations for now as real numbers. And what I mean by that is if I say, agent I's valuation function is, VI equals, 50 cents. Well, that's implicitly defining the function saying if agent I gets the toilet paper, then they get a utility of 50 cents, and otherwise they get nothing. Okay, so here we're going to assume that you have some value for the item being auctioned off, and if you don't get it, you just get utility 0. You don't care who else gets it if you don't get it. And so, we can cast single item auctions into our framework. Let's think about in this simple setting if we can come up with an auction that satisfies all of our desiderata. And if we can, then maybe we can start to have some hope that we can satisfy all of these desiderata in a fully general setting. Okay, so remember, to design a mechanism, we have to design two things. We have to design an allocation rule, and we have to design a payment rule. But I claim that if we want to satisfy all 4 of these desiderata, all of the action is going to be in designing the payment rule. Right, like if the allocation rule itself is sort of fixed for us, because if we want to be both dominant strategy truthful and allocatively efficient, then our hands are tied, right? I have to give the toilet paper to the person who reported that they wanted it the most, which is to say, my allocation rule must be to point to the person who reported the highest valuation, right? So there's no room for design there. The combination of allocative efficiency and dominant strategy truthfulness forces our hands there. But we do have some flexibility in thinking about what the payment rule should be. So maybe first, let's imagine what would happen if we didn't use any payments at all. Okay, so suppose I said, everybody tell me, everyone tell me a number, how much you value the toilet paper for, and I will just give it to the person who reported the highest number. What do you think? Like, is this going to be dominant strategy truthful? Why or why not? You can answer either in the chat or with your microphone. Yeah, so we have in the chat the correct answer, which is no. Everybody will, just try to think of the largest number they can possibly write down, right? Like if I'm not asking for payments, I'm just saying, tell me how much you value the toilet paper for, and I'll trust you. Then everyone, since they want the toilet paper, will just, furiously scribble down on the piece of paper the largest number they can possibly think of. They won't, actually report to me their true valuation. Okay, so we have to use payments here. So we can think about how our other desiderata constrain us, right? So we want our mechanism to be individually rational. So for people who don't get the item, we can't charge them anything, right? Like I can't say, sorry, you lost the auction, but give me $1. That would violate individual rationality. Okay, so why don't we try to fix the payment rule to be one that charges people nothing if they don't get the item. Okay, and similarly, individual rationality forces us to charge the person who gets the item something that is less than their reported valuation. Right? If you tell me you value the toilet paper at $2, I can't give it to you and then ask for $3. So let's try again. So what if I say, okay, if you don't get the item, you pay nothing. And if you get the item, you have to pay me exactly the value that you reported. Will this be an incentive compatible auction? What do we think? If I say the person who reports the highest valuation gets the item and pays me their reported valuation. Yeah, so the correct answer here is also no. And let's think about why that is, right? Like, suppose that you forgot to stock up before the coronavirus. You actually have no toilet paper remaining, and so you have an incredibly high valuation for this roll of toilet paper, and maybe you value this toilet paper roll at $15. Everyone else in the class was better prepared. They have a more standard valuation for toilet paper, maybe on the order of 50 cents. If you report $15, you will win the item, but you will have to pay me $15, and your utility will actually be 0, because on the one hand, you got something that was worth $15 to you. On the other hand, you had to pay me $15. You would be better off lying and misreporting your valuation downward. You should tell me, actually, your value for the toilet paper is only a little bit more than everyone else's, maybe 51 cents. Right? So long as you're still the high bidder, you're still going to get the item, but your payment will now be lower, right? And so you will be better off. And so this payment rule, what's called a first price auction, is actually sort of directly incentivizing people to misreport their valuations downwards. There's a question of whether this is still true in a blind auction, and it is. So first of all, what's a blind auction? Okay, maybe we all write our numbers on a piece of paper and hand them to the auctioneer. So in a blind auction, you won't have the luxury of knowing what everyone else bid, but okay, to think about what you should do, we have to model your beliefs. You might have some sort of estimate of the likelihood that your classmates stocked up on toilet paper, and so you might think that okay, you are probably the high bidder, maybe by some margin. So everyone will be sort of calculating in their own heads the probability that they would be the high bidder at different prices and thinking about how to shade their bids downwards, right? Like, there's a good observation in the chat that if you bid your true valuation, then no matter what, your utility at the end will be 0. It'll be 0 if you don't get it, and it'll be 0 if you do get it. And so you have to misreport. You have to shade your bid downward if you want to have positive expected utility. So that doesn't work. So let's try again. So what if we again say, okay, of course, if you don't get the item, you pay nothing. But if you get the item, you don't have to pay what you bid. You have to pay what the second highest bidder bid. You have to pay what the highest person who, the highest bidder who lost the auction bid. Right? So if I bid $2 and the other two bidders bid 50 cents and $1, then I'm asked to pay $1. Even though I bid $2 and was the high bidder. What do we think? Does a second price auction like this incentivize truthful reporting? There's a question, do the losers also have to pay? No, the losers pay 0 in all of the auctions we're thinking about. And then the conclusion of the comment is that yes, this is incentive compatible, and that's right. And so let's just think about this informally, and then we'll prove it in much more generality in the rest of the lecture. Okay, so suppose everyone has bid truthfully. Okay, and so the high bidder won the item and pays the second highest price. Let's just think, like, is there anything anyone could have done differently that would have gotten them higher utility? And the answer is no. So let's think about the high bidder, right? On the one hand, he could have raised his bid. He could have bid something higher than his true valuation. If he did that, he would still be the winner. And he'd still be asked to pay exactly the same thing because the second highest bid wouldn't have changed. So for the winner, raising their bid doesn't help them. They could also lower their bid. And as they lower their bid, there's sort of two possibilities, right? They could lower their bid a little bit, but such that they're still the high bidder. in which case, again, nothing changes. They continue to win the auction, and the amount they're asked to pay hasn't changed because the second highest bid hasn't changed. Or they could lower their bid so much that they are no longer the high bidder, at which point they're just strictly worse off because now they're losing the auction at a price they would have been willing to pay. They're losing the auction, now they're getting 0 utility instead of positive utility. Okay, so the high bidder cannot beneficially deviate by changing his bid. And how about someone who's lost the auction? Well, again, we can consider the two cases. If you've lost the auction, you could lower your bid. In that case, you would still have lost the auction and nothing would have changed. Or you could raise your bid. And here there's, again, two possibilities. You could have raised your bid a little bit, but not enough to win the auction, in which case, nothing's changed. You still lose the auction. Or you could have raised your bid so high that you are now the winner of the auction. But now you are asked to pay the bid of the person who is now the second highest bidder and used to be the first highest bidder, right? And that person bid more than your true valuation. And so although you've now caused yourself to win the auction, you're now asked to pay more than the value is, more than the good is worth to you. Okay, so once again, misreporting your bid upwards is not a beneficial deviation. Okay, so the mechanism is incentive compatible. That was sort of a hand-wavy argument, not a proof, but we're going to prove a much more general result of which this will be a special case. But does the sort of general argument for incentive compatibility make sense? Right, there's a good time for questions. Does it make sense to people why selling the item to the winner at the price that they bid does not incentivize truthful reporting, but selling the item to the high bidder at the price of the second highest bidder does induce truthful reporting? The second price auction also has a number of other desirable properties, right? Like we can observe some of them, right? So it's no deficit, right? Like we never pay anyone, people only pay us, right? And it's always individually rational by design. So in this single item auction case, the second price auction actually satisfies all of our desiderata. And it has a name, it's called the Vickrey auction. So there's a question, what if two players have the same highest value? Then we can sort of break ties arbitrarily. We can give it to either one of them, or we can randomize between them. And the second highest bid is equal to the highest bid. And so one of them is the winner, and they pay their bid in that case. One interesting thing to note, right, is that this sort of second price auction actually sort of implements the allocation rule and the payment rule for sort of the standard like TV auction that you might have seen, where there's like a auctioneer with a gavel, and the price is rising, and maybe people have little paddles that they wave in the air until the price gets above their willingness to pay, at which point they lower their paddle, right? And what happens in that auction? The person who has their paddle up the longest wins the auction. The auction ends when there's only one remaining bidder with their paddle up. And that means the person with the highest valuation wins the auction. And what do they have to pay? Well, they pay whatever the price was when the second to last bidder dropped out, because that's when the auction ends. And so in an English auction, in this kind of ascending price auction, the winner pays the second highest price. All right, one more question just to sort of get our heads around this stuff, right? So we seem to have gotten a big improvement from asking the winner to, from asking the winner to pay the first highest price to going to asking them to pay the second highest price. What if we go even further. What if we ask them to pay the third highest price? Do we get an incentive compatible mechanism? In that case, we don't, right? Right, like if I ask the winner to pay the third highest price, then there's someone who can beneficially deviate. In particular, the second highest bidder now has the opportunity to inflate his bid so that he's now the winner. And because he's only asked to pay the third highest price, if he does this, he goes from not winning the item to winning the item at a price that is still below his valuation. So the second price auction is sort of unique. Like this is sort of the unique price statistic that will make the auction truthful. The third highest price or the fourth highest price, none of these will work. Okay, so let's see if we can generalize to find the mechanism that has all of these nice properties, not just in the single item auction setting, but in the sort of fully general setting that we laid out at the beginning of the lecture. So here we're going to define an entire class of mechanisms. Okay, these are called the Groves mechanisms. And they're defined as follows. So again, just as in the single item auction setting, all of the action here is in designing the payment rule. Right? If we want our mechanism to be both dominant strategy truthful and allocatively efficient, we have no choice about what the choice rule should be. Right? The choice rule has to always select the alternative that maximizes the sum of the reported agent valuations. So anything interesting that happens is in the payment rule. And here's how the payment rule in the Groves mechanism is defined. Okay, and it's there's going to be this function h, which is left unspecified, which is what's going to make this a whole class of mechanisms, right? Any payment rule that has the following form for any choice of this function h will be a Groves mechanism. And the idea is the following. The amount of money that we're going to ask agent I to pay is equal to some function h of everybody else's bids. The crucial, it doesn't matter what h is. The crucial thing is that whatever h is, it depends on everyone else's reported valuations, but it does not depend on the report of agent I. Okay, we'll ask him to pay h of everyone else's bids minus the sum over all of the other players, other than agent I, of their value for the alternative that was actually selected. Okay, so this A star thing, this is the alternative that the Groves mechanism selected. It's the thing that maximizes social welfare according to the reported valuations, right? And the payment rule is just asking people to pay the difference between this arbitrary function of everyone else's valuations minus the sum of the utilities of everybody else, other than agent I, of their value for the alternative that the Groves mechanism selected. Okay, and this is a whole family of mechanisms because we haven't pinned down what h is. Note, because we haven't pinned down what h is, right, the payments that the Groves mechanism asks people to make could be positive or negative. There's no guarantee that these are going to be positive payments, right? Like h could be like the identically zero function. And so, there's going to be something that we have to pay attention to here. So the claim, right, is that although of course Groves mechanisms in general cannot satisfy, always all of the properties that we want. Like in particular, we've already noted that, if we made a bad choice of h, then they wouldn't satisfy the no deficit property. The claim is that any Groves mechanism already satisfies some of the nice properties we wanted. And if we want to satisfy all of them, maybe we can try to do that by first establishing good properties that any Groves mechanism satisfies, and then trying to pick an h function that causes some particular Grove's mechanism to satisfy the other nice properties that we want. And so the claim is that, remember, there were these 4 nice properties we wanted. Any Grove's mechanism, no matter how we pick H, already satisfies 2 of them. In particular, it's always allocatively efficient, and it's always dominant strategy incentive compatible. Okay, and it's allocatively efficient by definition, right? Like our choice rule, the choice rule we wrote down was just the choice rule that selects the alternative that maximizes social welfare. And so the only thing we really need to prove here is that the Grove's mechanism is dominant strategy incentive compatible. And so let's do that. So remember what we need to prove. We need to prove that for any agent I, no matter what everyone else reports, and no matter what misreport VI prime that agent I might consider making, agent I will have only higher utility if they correctly report their valuation function than if they report something else like VI prime. Okay? Now we can write down player I's utility as a function of their report, right? Like in particular, it's going to be their valuation for the alternative that the mechanism chooses given their report, plus, or rather, minus the payment they're asked to make, right? And if we just remember what the payment rule is for Grove's mechanisms, subtracting off the payment corresponds to adding the sum of everyone else's valuation for the alternative that was chosen minus this arbitrary function h of everyone else's reports. Okay, and remember here, A star, the mechanism, the outcome, the alternative chosen by the Grove's mechanism, is by definition the alternative that maximizes social welfare given the report VI prime that agent I made, right? Like the mechanism doesn't know agent I's true valuation function VI, it only knows the report. And so the alternative that the mechanism is going to choose is the one that maximizes social welfare given the report, right? So this is how agent I can potentially affect things. By changing her report, she can change which alternative the mechanism chooses. So, the problem that agent I is facing is to decide what valuation function VI prime she should report so as to maximize this function. And note that we don't know much about this function h, right? Like h can be arbitrary, but we did specify that whatever h is, it's a function only of everybody else's reports. Like the crucial thing about h is that it's independent of player I's own report. Okay, so remember that players want to maximize their utility given here, but they have no control over this function h, because if they misreport their valuation function, it won't change the value of this function h, which after all depends only on other people's valuation functions. And so choosing the report to maximize this whole thing is equivalent to choosing the report that maximizes just the part of player I's utility function that they have control over, right? Just the part that depends on the alternative chosen by the mechanism, A star, which is chosen as a function of their report. So a player who is going to pick a report VI prime to maximize her own utility is just going to pick it's just going to pick the report VI prime that maximizes the first part of her utility function, which is just the sum of everybody's utility function, of everybody's valuation function for the alternative that's actually chosen, right? Because if I want to maximize some function that has 2 terms, the first of which I can control and the second of which I can't control, I might as well ignore the term that I can't control. It'll be the same no matter what I do, and just maximize the part that I can control. Okay, but note that the mechanism is choosing A star exactly to maximize the sum of people's valuation functions as they are reported. So if I want to maximize sort of the sum of the true valuation functions, including my own actual valuation function, and the mechanism is going to maximize the sum of the reported valuation functions, then our incentives are entirely aligned, right? Like by definition, if I truthfully report, then the alternative chosen, A star, will be the one that maximizes my utility function, because that is explicitly what the mechanism is designed to do. And if I misreport, it might choose something else. And that establishes that it's a dominant strategy for all agents to report truthfully. Okay, does that make sense? Are there any questions about that? So there's a question, doesn't this require person I knowing what the other people will select? It does not, right? Person I doesn't care whether the other people have reported truthfully or not, right? No matter what valuation functions the other people have reported, what the mechanism is going to try to do is it's going to try to maximize the sum of everyone's reported valuation functions. What the payment rule has done is it has made person I's utility function equal to the sum of person I's true valuation function plus everybody else's reported valuation function. And what that has done is it's entirely aligned the incentives of the mechanism designer and of agent I. Right? Agent I wants to maximize exactly the thing that the mechanism will maximize if agent I reports truthfully. It's a good question. Any other questions? Right, it's important, since we want to establish dominant strategy incentive compatibility, that we establish that it's a best response for agent I to report truthfully no matter what anyone else does. And this is exactly what the Groves mechanism accomplishes. Another question, does this require no collusion as well? So, okay, let's try to parse the word require. So remember that the way a dominant strategy is defined is that no matter what anyone else does, there should be no way for you to benefit by unilaterally deviating. So on the one hand, there's no like hidden assumption here in the theorem, like the theorem is what it is, the mechanism is dominant strategy truthful. On the other hand, the guarantee of dominant strategy truthfulness only protects against unilateral deviations, and it doesn't promise at all that sort of a collusive group of people might not be able to benefit by, getting together and coordinating their misreports. And in fact, there's a problem on the homework that will ask you to give an example of when mechanisms like this are not robust to the possibility of people colluding. Good question. Any other questions before we go on? Okay. And just to reiterate, the reason we get truthfulness here, like the cleverness that's going on here, is that what the payment rule has done, right? What this payment scheme has done is it has, by having this term that corresponds to the sum of everybody else's reported valuations for the alternative chosen, it has explicitly aligned the incentives of the agents and the mechanism designer, right? Like the agents now, when they take into account their payments, are getting utility equal to the social welfare. And the mechanism's trying to maximize social welfare. And since the agents are getting utility equal to the social welfare, they also want to maximize social welfare. That's why it gets dominant strategy truthfulness. Okay. Now, of course, remember the Groves mechanism does not uniquely specify a mechanism, right? There's this thing that is left unspecified, this function h. And we proved that no matter what h is, the Groves mechanism is allocatively efficient and dominant strategy truthful, but it doesn't necessarily satisfy the other properties we wanted. So we'd like to make some clever choice of h. And maybe let's think about this again in the context of a single item auction. right? So our alternative set is just the set of agents who we're going to give the toilet paper to. And so let's try something simple, right? So like maybe the simplest possible choice is to just take h to be the sort of identically 0 function. What if h is 0 no matter what people report? Okay, and we can think about what would happen if we have 2 bidders. Okay, so say the first bidder has value, $5 for the toilet paper. The second bidder has value $8. Well, the mechanism is dominant strategy truthful, and so people will bid truthfully, and so the mechanism will give the toilet paper to the person who has the highest valuation. It's the second bidder. He's got valuation 8. And the resulting social welfare is 8, right? Because the social welfare is just the sum of everyone's valuations for the chosen alternative, and well, like bidder 1 has valuation 0 for the chosen alternative because he didn't get the toilet paper. Bidder 2 has valuation 8. And what the payment rule says is, well, right, we're supposed to pay bidder 1, or rather, bidder 1 is asked to pay h of v2, which is 0, minus v2. Okay, so bidder 1 is asked to pay minus $8, meaning we pay bidder 1 $8, and bidder 2 is asked to pay $0. And so it's sort of clear why the mechanism is dominant strategy incentive compatible. Both players in the end have utility 8, right? Bidder 2 has utility 8 because he actually got the toilet paper and wasn't asked to pay anything. Bidder 1 has utility 8 because even though he didn't get the toilet paper, we handed him $8. And this is sort of maybe making it clear why, how the mechanism is getting dominant strategy incentive compatibility. It's maximizing social welfare, and it's making payments to guarantee that everyone's utility is equal to the social welfare. But of course, this mechanism is not no deficit. Like, this is a mechanism that's sort of getting incentive compatibility sort of by bribing people, right? Like, this is not a mechanism we want to run. It's expensive to run. Somehow the way we got incentive compatibility is by bribing bidder 1 not to deviate. And so, okay, like, what this is showing is that certainly if we want all of the 4 properties we laid out, in particular the no deficit property, a bad choice of h is not going to give this to us in the Groves mechanism. But there's the question, like, is there a good choice of h? Can we pick some function h that will, of course, retain the 2 properties that we know that all Groves mechanisms have, allocative efficiency and incentive compatibility, but that will give us the no deficit property without breaking individual rationality? Okay, so that's what we want to do. Any questions about this example? Okay. So finally, I want to talk about the Vickrey-Clark-Groves mechanism, or the VCG mechanism, which is sort of, the thing we've been building up to. Vickrey, Clark, and Groves, by the way, won the Nobel Prize for the development of this mechanism. And the VCG mechanism is nothing but a particular instantiation of the Groves mechanism. And so the VCG mechanism is ultimately going to be a mechanism that solves the mechanism design problem we set out at the beginning in entirely full generality, while satisfying all 4 of the desiderata that we laid out. And it's just going to be the Groves mechanism with a particular clever choice of h. Okay, so what is that choice of h? The function h that the VCG mechanism chooses is the following. It's just the sum over all of the players other than player I of their valuation for the alternative that the mechanism would have chosen had bidder I decided not to participate in the mechanism. Okay, let's parse that. It's the sum over all of the other players, J, not including player I, of their valuation for this alternative that I've written A star minus I, which is defined to be the alternative that the mechanism would have chosen had player I not participated. A star minus I is the thing that maximizes social welfare if we consider only the n-1 agents other than I. Okay, so just reminding ourselves what payment rule we get when we plug that into the Grove's payment rule. The VCG mechanism is going to ask each agent I to pay the difference between how happy in aggregate the other players would have been had player I not participated, right? The difference between the sum of all of the valuation functions evaluated at the alternative that would have been chosen had player I not participated, minus the sum over all of the other players of their valuation for the alternative that was actually chosen. Okay? And the intuition here is that what the VCG mechanism is asking every player to pay is the negative externality that she imposes on the market, right? Had she not participated, the Grove's mechanism would have chosen a different alternative. It wouldn't have tried to maximize social welfare, including her. It would have tried to maximize social welfare, not including her. Given that she did participate, it chose a different alternative, which potentially made the other people in the market, in aggregate, less happy. And the VCG mechanism asks everyone to pay this difference, sort of how much less happy everyone else is in aggregate because player I participated. All right. So we're going to prove that the VCG mechanism has the remaining two nice properties, but I just want to pause and take a moment to make sure that people understand what the payment rule is here, because that's really the sort of crucial thing. That's what's doing all the work. So are there any questions about this payment rule and how it's defined? All right. So what we're going to show is that the VCG mechanism actually satisfies all four of our desiderata. We already know, of course, that the VCG mechanism is allocatively efficient and dominant strategy incentive compatible. And that's just because it is a Grove's mechanism, right? Like the VCG mechanism is just a Grove's mechanism for a particular choice of H. And we proved already that for all Grove's mechanisms, no matter what H is, you get allocative efficiency and dominant strategy incentive compatibility. So there's nothing else to prove here. What we need to prove is that the VCG mechanism, in addition, is individually rational and no deficit. Okay, so let's do that. So first, the claim is that the VCG mechanism is individually rational, which just means that nobody can ever come to harm by truthfully participating in the mechanism. Okay, what we need to show is that for every agent I, if they participate truthfully, their utility is always non-negative. I never ask anyone to pay more money than they value the alternative that I chose. Okay, so just sort of instantiating that natural goal in our setting, what we need to prove is that for every agent I, their utility for the chosen outcome, which is just, remember, their value for the chosen outcome minus the payment that they're asked to make, and substituting in the VCG payment rule, subtracting off the payment that they're asked to make is just adding the sum of everyone else's valuation for the chosen outcome and subtracting the sum of everyone else's valuation for the outcome that would have been chosen had player I not participated, right? We need to show that this utility function is always non-negative, no matter what. Player I can never come to harm. And equivalently, just by, like adding the last term to both sides of this inequality, what we need to show is that if I look at the sum over all of the players of their value for the chosen outcome, this is only larger than the sum of all of the players other than player I of the outcome of their value for the outcome that would have been chosen had player I not participated. But this is true, right? Like, we haven't assumed much about these valuation functions, but the assumption is that they're non-negative, that if I give you something that you have non-negative utility. And because of that, we can observe the following, right? Like, the mechanism could have chosen outcome A star minus I, even with player I participating, right? And that would have gotten some social welfare, right? The sum over all of the players I of their value for the alternative A star minus I. And this is only larger than the sum of the values of all of the players other than player I for this chosen alternative, because in the worst case, right, player I had utility 0 for this alternative. And if we didn't satisfy individual rationality, this would have to be strictly larger than the sum over everyone's value for the alternative that was actually chosen, A star. But that's a contradiction, because what's A star? A star is explicitly the alternative chosen to maximize social welfare, right? Like, because the mechanism is allocatively efficient, we've chosen the alternative that maximizes social welfare. Or to say all of this another way, we decided to maximize social welfare. If the mechanism chose A star instead of choosing A star minus I, it has to be because A star has higher social welfare than A star minus I. And that's enough to establish individual rationality. And there's only one more thing to prove, right? We want to show that the VCG mechanism is also no deficit, that we never lose money by running the VCG mechanism. And in fact, we can show something even stronger than that, right? The no deficit property only requires that in aggregate we not lose money. But what's actually true of the VCG mechanism is that the payments are all non-negative. We never have to pay anybody, right? We only ask people to pay us. Okay, of course, if we only ask people to pay us, then our mechanism is only taking in money. It's not giving out money in aggregate as well. And so to prove this, let's just remember what the payment rule is. Okay, so once again, the amount of money that we ask each person to pay is the difference between two things, right? On the one hand, the first term is the sum of everyone else's valuation for the alternative that would have been chosen had player I not participated. And on the other hand, we're subtracting off the sum over everyone else's valuation for the alternative that was actually chosen. And of course, this is non-negative whenever the first term is bigger than the second term. But this is always the case, right? Because, what's the first term here? It's the social welfare of all of the players, excluding player I. And by definition, A star minus I, the alternative that would have been chosen had player I decided not to participate, right? By definition, this is the alternative that maximizes this sum. It's the alternative that maximizes the social welfare of everyone other than player I. And so by definition, the first term has to be bigger than the second term. And so the payments are all non-negative. Okay. So we've shown what we wanted to show about the VCG mechanism. Any questions before we have a couple of concluding thoughts? Okay, so I just want to remark, right, that sort of it certainly seems like we've given an extremely powerful result here, right? We defined an incredibly general setting, right, that could capture, basically anything in which you're choosing amongst alternatives, not just auctions, but elections. We could choose candidates, deciding on public goods, should we build libraries, deciding on policy decisions. And in this fully general setting, we've demonstrated a mechanism that satisfies all of the desiderata that we laid out, right? It incentivizes people to report truthfully. It chooses the outcome that sort of makes people the happiest. It's safe for people to participate in. It never requires us as the mechanism designer to spend any money. Sometimes it might even make us a profit. And so, you might reasonably ask, can we just, end the class here? Like, is this all there is to know about mechanism design? And it's not a crazy question. I mean, this was like a big result, and there's a Nobel Prize in economics that was devoted to this result. But there are still some things that it leaves to be desired. Right? So first of all, it chooses a good outcome if what you care about is social welfare, if what you care about is maximizing sort of aggregate happiness. But that's not necessarily the only thing you might want to maximize, right? Like something that people running auctions often want to maximize is their own profit. And the VCG mechanism doesn't do that. There's other things you might want to maximize as well. And maybe more to the point for this class, because this is an algorithmic game theory class, the VCG mechanism is not in general computationally efficient. Right? Like we sort of swept this under the rug, but like the very first step of running the VCG mechanism before we even think about computing the payment rule is to choose the alternative that maximizes social welfare. Well, how do you do that? I mean, okay, if it's a single item auction, it's very easy. You just find the person who reported the highest bid. But in general, it can be complicated, right? Like if it's like a combinatorial auction, if I've got, millions of items and I want to partition them amongst millions of people, okay, all of a sudden, like I can't just expect to solve this problem with exhaustive search. Like I've got a real computational problem. And in fact, it's a problem of the sort that in real auctions is often NP hard, a problem that we sort of cannot hope to solve exactly in polynomial time efficiently. And okay, like we have solutions in computer science for problems we can't solve exactly in polynomial time. We can try to approximate them. But it turns out that the VCG mechanism is extremely brittle to these kinds of approximations, right? Like when we proved that the payment rule was dominant strategy incentive compatible, we crucially used the fact that the alternative that we chose is the one that exactly maximized social welfare. And if we merely found something that was within 1% of maximizing social welfare, the VCG payment rule might sort of have enormous disincentive for people to report truthfully. So, there was this hidden assumption of sort of unlimited computational power that we're going to want to think about. Anyways, that was the VCG mechanism. We'll think about these other things next class. I'm going to turn off recording now, but I'm going to stick around to answer questions if anyone has any. All right. So for everyone else, stay healthy. See you next class. Keep washing your hands.